So, picture this. If I hold a bullet in my left hand, right, and I have a high-powered rifle in my right hand, aimed completely horizontally over this massive flat field.
Right, a perfectly flat plane.
Yeah, perfectly flat. And I drop the bullet from my hand at the exact same millisecond that I pull the trigger on the rifle.
Mhm.
Which bullet hits the dirt first? I mean, the one dropping 3 feet from my hand or the one fired it's literally hundreds of miles per hour?
It's such a classic setup,
It is. And counterintuitively, physics dictates they actually hit the ground at the exact same millisecond.
which is wild.
Today, we're going to find out exactly why that happens. You are joining us for a deep dive into our stack of source material
Mm.
to um, decode what physicists call the architecture of motion. Specifically, we're breaking down one-dimensional and two-dimensional kinematics.
Yeah.
And look, I know. Okay, let's unpack this. The word kinematic sounds,
Oh, absolutely. It sounds incredibly intimidating.
it sounds like something you need a lab coat and a chalkboard to even discuss. But really, the concepts we are looking at in these sources, they're basically the invisible source code of just, well, everything that moves around you.
Yeah, that's exactly right.
We're going to take you from the messy physical reality of objects flying through the air all the way down to the pristine abstract mathematical grid that actually dictates their path.
And that is a crucial point for you to keep in mind as we go through this material today.
Right.
The goal here isn't just to memorize a bunch of formulas or crunch numbers.
Definitely not.
It's to fundamentally understand the actual mechanism behind the motion.
Hmm.
We want to reveal how seemingly erratic or chaotic movement in our three-dimensional world is actually governed by a set of incredibly elegant, predictable rules.
Like a hidden framework.
Exactly. Once you see the scaffolding, you realize that nature is following a very strict script.
I love that. So, to make this tangible, to get us out of the textbook and into the real world, our sources start with a really highly visual example.
Right? The dirt bike.
Yeah. Picture a dirt bike. We have got a rider gunning the engine, hitting a steep ramp, and just launching high into the air over a gap.
It's really the perfect starting point to visualize this stuff.
Why is that?
Well, when you observe that dirt bikers jump, you have to realize the motorcycle is doing two entirely distinct things at once.
Okay.
It is not moving exclusively on the vertical axis, meaning, just straight up and down like an elevator,
Right.
nor is it moving strictly on the horizontal axis, just flat forward like a car on a highway. It is moving through both of those planes simultaneously.
Both at the exact same time.
Right. And that simultaneous movement is the defining characteristic of projectile motion in two dimensions.
So the arc itself.
Yeah, that beautiful, sweeping, parabolic path the bike travels through space is what physicists call its trajectory.
We all know that parabola, right?
Yeah.
That arc. I mean, we see it when we throw a baseball or toss a crumpled up piece of paper into a trash can.
All the time.
But here is the big aha moment from our source material. This absolutely blew my mind when I first read it, and it really goes back to that bullet question I posed at the start.
Mhm.
The source actually calls this the secret to kinematics. It is a concept called the principle of axis independence.
The principle of axis independence is basically the cornerstone of everything we are discussing today.
It really is.
It states that motion along the x-axis, so the horizontal plane moving left to right, and motion along the y-axis, the vertical plane moving up and down, are completely 100% independent of one another.
Wait, like entirely?
Entirely. They do not affect each other at all.
Yeah.
The universe essentially treats them as two separate events happening in the same place at the same time.
Which is just so counterintuitive. Because you look at the dirt bike jump and your brain processes it as one big combined fluid event.
Of course it does, yeah.
But to help you visualize what is actually happening mathematically, imagine this. Imagine shining a massive, powerful spotlight straight down from the sky onto that dirt biker while they are in midair.
Oh, that's a great way to think about it.
Right. That light casts a stark shadow on the flat, perfectly level ground down below.
Yeah.
If you only watch that shadow moving across the dirt, that shadow is our x-axis. According to the sources, that shadow is moving forward at a perfectly constant velocity.
Exactly constant.
The acceleration on the x-axis is exactly zero. The shadow does not speed up, it does not slow down, and crucially, it does not care at all that the actual physical biker above it is flying 40 feet into the sky.
No, it doesn't. Or plummeting back down to the earth, for that matter.
Right.
The horizontal motion is completely blind to the vertical motion because, as the source points out, gravity is highly specific.
Very specific.
Gravity, which is a constant downward acceleration of roughly negative 9.8 meters per second squared on Earth.
Right.
It only pulls on the y-axis, it only operates vertically, it completely, totally ignores the x-axis.
Wait, I have to stop you there. Are you seriously telling me that horizontal speed has zero impact on gravity? Because, I mean, if a dirt bike is launching off a ramp at like 60 miles an hour, shouldn't that massive forward momentum somehow fight against the downward pull? Doesn't going really fast forward buy you more time in the air?
It feels like it should, doesn't it?
It really does.
Our intuition tells us that speed is power, and, power should overcome gravity. But that is the illusion of the parabola.
Illusions of the parabola.
Yeah, forward momentum cannot cancel out downward acceleration because they are operating in literally different dimensions of the grid.
Oh, wow.
Think of it like two different bank accounts.
Okay, I'm tracking.
Spending money from your horizontal account does not change the balance of your vertical account at all.
Ah, I see.
Gravity is only deducting from the vertical account. So the biker's shadow glides forward at a steady pace, while gravity ruthlessly pulls the physical bike up and then down entirely on its own schedule.
So we have this shadow moving at a constant speed forward,
Yeah.
and the actual bike being pulled up and down by gravity. How do physicists actually use that information? Like, if the two axes are entirely separate, how do we predict where the bike is actually going to land?
Well, this brings us to what the sources call the kinematic framework.
Okay.
Because these two axes, the x and the y, do not interact or interfere with one another, they form a perfect 90-degree angle.
Like a corner.
Exactly. You can treat them as two sides of a right triangle.
Oh,
This means you can use basic right angle trigonometry to kind of stitch them back together and find out exactly what the bike is doing at any given second.
so instead of looking at the messy reality, we just build a triangle out of the shadow speed and the falling speed.
Precisely that. If you want to know the overall magnitude of the bike's speed, like the raw miles per hour it is traveling through the air, use the Pythagorean theorem.
A squared plus b squared equals c squared.
You got it. You take the horizontal velocity, you take the vertical velocity, and you combine them to find the hypotenuse.
Okay, that makes a lot of sense.
And if you need to know the exact angle of the trajectory, like the direction the bike is pointing, you use an inverse tangent function.
Wow.
The framework allows you to dissect the motion, analyze the horizontal and vertical entirely separately using their own specific rules, and then elegantly recombine them to see the full picture.
Okay, so that is the foundational principle, axis independence.
Yes.
But I want to know what happens when we push this principle to a violent extreme. Let's move from a dirt bike on a track to a high-speed projectile.
A great pivot.
Let's look at the scenario in our sources where we fire that bullet from the beginning of the show.
Okay, and what's fascinating here is how the principle of axis independence simplifies an event that happens so fast the human eye cannot even track it.
Right, so here's the scenario laid out in the slides. We have a gun positioned exactly 1.5 meters above the flat ground.
About shoulder height.
Yeah, and it is aimed perfectly, mathematically, horizontally. The trigger is pulled, and a bullet is fired with a massive initial horizontal velocity of 255 meters per second.
That is incredibly fast.
Super fast. The question the source asks is, how long is that bullet in the air before it hits the ground?
Well, because the bullet is fired perfectly horizontally, right? All of that explosive energy, all 255 meters per second of it, is applied strictly to the x-axis.
The shadow.
Yes. This means its initial vertical velocity is a flat 0.
Wow.
At the exact microscopic millisecond it leaves the barrel, it is not moving up and it is not moving down.
It's just like the dirt bike's shadow. It's just moving purely forward.
Yeah, and because of that, finding the time it takes to hit the ground is surprisingly simple. We only need to look at the y-axis.
The vertical plane.
Right, we only look at the vertical plane. We have an object starting at a height of 1.5 meters with 0 initial vertical speed just being pulled down by gravity.
So the speed just doesn't even factor in.
The massive forward speed does not matter. The equation the sources provide allows us to isolate the time based entirely on gravity's pull from 1.5 meters.
And when you run that specific drop, the bullet hits the ground in just 0.56 seconds.
Literally half a second.
Half a second. And the wild part is that massive 255 meters per second horizontal speed didn't factor into the drop time at all.
Not even a little bit.
It just dictated how far away the bullet landed.
Yeah.
It could have been moving at 10 meters a second or 1,000 meters a second. If it's fired perfectly flat, it hits the dirt in 0.56 seconds.
It simply covers more ground horizontally while gravity does its vertical work at its own constant pace.
Okay, but again, let's talk about reality. A shooter is human.
Right.
What if the launch isn't perfectly flat? What if, as they pull the trigger, they breathe heavy or bump the rifle up just a tiny, tiny bit?
Well, the sources anticipate that exact reality with a second scenario, which is the angled launch.
Okay.
Let's say the same rifle, firing at the same massive speed of 255 meters per second, is tilted upward at an angle of just 10 degrees relative to the horizontal.
Just 10 degrees. I mean, that is barely a twitch of the shoulder.
It is a minute adjustment,
Right.
but mechanically it changes everything. Because we are now introducing an angle, the initial velocity is no longer strictly on the x-axis.
Wow.
The bullet now has an initial vertical velocity. A portion of that explosive powder is now pushing the bullet up into the sky.
So it's not starting at 0 anymore.
No, it's not. We have to derive those components using trigonometry, taking the sine of that 10-degree angle to figure out exactly how much energy is being applied to the y-axis.
So now the y-axis has its own starting energy, its own upward push to fight against gravity instead of starting at 0.
Exactly. And that upward push is fighting gravity for a much longer time.
Makes sense.
When we plug that new vertical energy into the kinematic equation for maximum height, the result is stunning. That tiny 10-degree tilt sends the bullet soaring to a maximum trajectory height of 100.04 meters.
Are you kidding me?
100 meters.
That is unbelievable. From a perfectly flat shot that drops 1.5 meters to the dirt in half a second, to a shot that arcs 100 meters into the sky.
Yeah.
That is more than a football field straight up. All from a 10-degree shift.
It perfectly illustrates how incredibly sensitive the system is. A slight shift introducing a y-axis vector changes the entire architecture of the event.
Because it triggers that vertical bank account.
Yes. The x-axis is still doing its independent thing, pushing the bullet forward across the field, but now the y-axis is playing a massive, prolonged tug-of-war with gravity.
Okay, the shadow analogy works perfectly for the overall jump.
Sure.
It makes sense for finding the max height or, the final drop time. But what if things go wrong?
What do you mean?
Like, what if we are tracking a missile or that dirt bike engine stalls midair and we need to know its exact coordinate at second 2.4 to place a safety net? Basic algebra seems way too clunky to track that live.
Yeah.
How do physicists map the motion continuously?
That requires upgrading our mathematical tools entirely. We have to move beyond isolated algebraic equations that just give us the peak or the end of the journey.
So what do we use?
To track motion continuously at any microscopic slice of time, we have to enter into vector space and the calculus of motion.
Now, here is where it gets really interesting. Our sources introduce this concept of position vectors.
Yes.
Instead of running separate, disconnected equations for the horizontal side and the vertical side, we map a specific point in space using a single unified language.
A single equation, yeah.
The sources use what physicists call standard unit vectors. They assign an I to represent the horizontal direction and a J to represent the vertical direction.
Vectors are essentially data container.
Okay.
Standard algebra breaks down when objects move in two directions at once because a regular number can only tell you how much. A vector tells you how much and in what direction simultaneously.
That is so efficient.
It is. By using I for horizontal and J for vertical, we create a way of writing down an object's exact GPS address in space at any given moment. It elegantly bundles the two independent axes into one unified expression without mixing them up.
So I is the horizontal DNA and J is the vertical DNA.
Exactly.
They travel together in the equation, but they never blend.
Yeah.
And this is where we bring in calculus.
Yeah.
Because calculus is essentially the mathematics of change, right?
It is the ultimate tool for tracking a dynamic system. Think of calculus like a freeze frame camera.
A freeze frame.
Right. If you start with your position vector, which tells you where the object is on the grid, and you want to know how fast that position is changing at one exact millisecond,
Yeah.
you take what is called a derivative. You take the derivative of the position with respect to time.
And taking that derivative peels back a layer.
Right.
Revealing the exact velocity at that frozen fraction of a second. Not an average speed over the whole trip, but literally the speedometer reading at that exact moment.
Exactly, the instantaneous velocity. And the pipeline goes a step further. If you use calculus to take the derivative of that velocity, if you peel back another layer, you are calculating how fast the speed itself is changing at that exact millisecond.
which reveals the instantaneous acceleration. So it is just a direct pipeline,
Hmm.
position down to velocity and velocity down to acceleration.
It's a beautiful process. And to see this mechanism in action, the slide deck walks through a derivation of an abstract particle.
Right, the 32I stuff.
Yeah. The sources give us a complex equation for the particle's position involving time variables, t, and those I and j vectors,
Yeah.
like 32e plus 40t minus 5t rested.
Sounds like a mouthful.
It does. But when they take the first derivative to find the velocity, the math shifts. The time variables shrink.
Okay.
And when they take the second derivative to find the acceleration, the math does something genuinely beautiful. On the I side, the horizontal side, the derivative zeroes out entirely.
Meaning there is zero acceleration pushing horizontally. The shadow is just gliding at a constant speed, exactly like we talked about.
Exactly. And on the J side, the vertical side, the calculus strips away all the remaining time variables, leaving nothing but a constant negative number.
Which is gravity.
Yes.
The calculus essentially acts like an X-ray machine. It strips away the movement, it strips away the time, until we reach the fundamental, unchanging engine driving the vertical motion, which is literally just the downward pull of gravity.
It proves mathematically what we discussed conceptually.
That's amazing.
The sources then push this into complex 2D kinematics, showing how you can start with known initial velocities and accelerations, plug in a specific time, like 4 seconds, and use vector matrices to find out exactly where an object is and how fast it's moving.
Right.
But the arithmetic itself isn't what matters here. I want to highlight what I think is the most profound takeaway from these final slides.
So what does this all mean for us?
Well, it means the mathematical grid is universal. Yes. By simply assigning an I to the horizontal and a J to the vertical, scientists collapse the chaotic, unpredictable three-dimensional universe onto a flat, understandable piece of paper.
Wow.
The exact same mathematical rules, these precise calculus pipelines we just discussed, govern a dirt biker flying through the muddy air, and they perfectly scale to map the subatomic motion of an abstract particle in quantum vector space.
That is just,
Yeah.
it's mind-bending.
The architecture is exactly the same. The universe uses the same source code for the macro and the micro.
It really does give you a sort of X-ray vision for the physical world, doesn't it?
Yeah.
As we wrap up this deep dive, I just hope that the next time you see a baseball thrown across a field or, a biker launch off a ramp, you don't just see the aesthetic arc of the motion anymore.
Right, you'll see the matrix.
Yeah, you will see those independent X and Y axes working simultaneously. You'll look at the ground and see the imaginary shadow moving steadily forward, completely unbothered, while gravity plays its isolated tug of war on the vertical plane. It fundamentally changes the way you look at everyday reality.
It certainly deepens the appreciation. But if we connect this to the bigger picture, this raises an important question for you to take away.
Okay.
The source material we reviewed today made one very specific, very crucial assumption. When we calculated the bullet dropping in 0.56 seconds, the text explicitly stated ignore air resistance.
Ah, right. Ignore air resistance.
Yeah. We assumed a pristine theoretical vacuum where horizontal velocity remains perfectly constant forever, but the real world is messy.
It's very messy.
The real world is full of atmosphere.
Right. There's wind, there's drag, there are weather conditions.
So I want you to ponder something. What happens to this pristine, elegant mathematical architecture when we introduce a third dimension?
The z-axis.
Right. What happens when we add the z-axis representing depth and crosswinds blowing across the field? Or what happens when aggressive air friction, like the fluid dynamics of our atmosphere, actually starts pushing back on that supposedly independent x-axis, physically slowing the bullet's forward shatter down?
The independence gets a lot more complicated when the air itself is acting like a physical wall.
How much more complex does the calculus of our physical reality become once we remove the vacuum? The physics we discussed today are the scaffolding, but the atmosphere is the wild card that makes engineering and applied physics so incredibly challenging.
It's a whole new layer.
The elegance of the grid has to fight against the chaos of fluid dynamics.
That is a phenomenal question to leave off on. We have seen the underlying grid, the perfect right angles holding our world together, but the real world always throws a wrench into the works.
Always.
Thank you for joining us on this deep dive into the source code of motion. Keep looking for those hidden rules. Keep questioning the mechanics of what you see around you. And remember, even the most chaotic, high flying jump has a shadow moving at a constant speed, completely ignoring gravity, right there on the x axis.